giving you just more examples of this so you can see this. Here is a microacceptor. That's an amide. So can amides do this? Yes, amides have a carbonyl here. So as long as the carbonyl is adjacent to an alpha beta unsaturated system here, in this case a double bond, it can be a microacceptor. Okay, so here is my nucleophile. The question is, what is the most acidic proton? It's going to be this guy here, flanked by these two carbonyls. So this guy should attack this carbon, and notice that's what we get. Very simple. Okay, now this is a little bit more complicated, right? So again, this is my alpha beta unsaturated system, double bond, carbonyl. Okay, here I have a carbonyl, CH2 nitrile. Remember I talked on Monday and I said I want you guys to think about, in general, any group that has resonance stabilization. We talked about nitrile ketones, nitrile esters. I talked about dicyanylmethane, how that does that. I also talked about nitro groups. This could be a nitro group. This methylene is acidic. And because it's acidic, it's going to get deprotonate to make a nucleophile. That nucleophile will now attack that beta carbon. Okay? So again, I get this product. And again, so the key part here is to do one of two things. Again, identify the microacceptor first. Identify where the electrophilic carbon is, if it's 1,2 versus 1,4 addition. In the case of a microreaction, it's always going to be beta position. And then finally, figure out which is your most acidic proton to generate the enolate that becomes your nucleophile. Okay, and all we're doing is basically taking this nucleophile and attaching it here. That's all we're doing. Taking this nucleophile and attaching it here. Okay, so again, it's very simple. Now, it turns out this microreaction is has been used for a very long time in many syntheses. Here is an alpha beta unsaturated system. Okay, so here I have a double bond here, conjugated to this carbonyl. Okay, and here I use, I have basically a 1,3 diketone system that is in a cyclopentanone ring. So here I have a carbonyl, here I have a carbonyl, I have a methyl, but I have a hydrogen here that makes this hydrogen acidic. So recognize this is my beta carbon, this is because this is my microacceptor. And now I'm looking at what is my most acidic proton here. The most acidic proton is that proton in between these two carbonyls. So I expect that the base comes in, abstracts this proton to make a nucleophile. And now that I have that nucleophile will attack the beta carbon. Notice that's that bond formed here. Okay. What's interesting about this, ladies and gentlemen, is that eventually this can get, in further steps down the line, it can be converted to the hormone estrogen. Okay, so what's really interesting is that a lot of the stuff I'm talking about in the past couple of chapters and in this chapter, we're going to start seeing its synthetic potential. And this is one example of its synthetic potential, is the example of potentially making a steroid, a hormonal steroid. Now, I don't know if any of you guys tried this, but why don't you take a few minutes to try this, and then I'll go over it with the document count. Okay. So what I want you guys to do, don't talk about it. I want you guys to look at this and start thinking about some of these reactions. So, you know, what is the structural intermediate for compound 8? What does that look like? What does the compound look like for compound B? What does C look like? What does D look like? Okay. All right. So let me. I had to open up my other computer, so. Okay. So the first part, you guys should all see my document camera, correct?
Yes.
Okay. So A is basically taking the amine and treating it with this microacceptor.
I don't see the document thing. I just see your screen.
Okay. Let me turn off the stop square.
There we go.
Okay. That's what I was afraid of, because now I can't see the problem, but that's okay. That's why I opened up my other computer. Okay. And please talk to me, because I have my other computer open. I can't see what I'm writing, but if it doesn't all show up. But again, this guy should attack this carbon. I get a carbon, and so I should get a structure that looks like that. Okay. Now I'm going to show it in this fashion. So this is structure A. Here I have the second reaction. Can anyone tell me? What do you think is going on here?
I think that nitrogen is going to attack. And then kick off the PR?
Yep. But I was really asking you, and I want you guys kind of remind yourselves, and I don't know if you guys learned this, but again, I definitely teach this when I teach substitution chemistry in the first semester. But this is a great SN2 alkyl halide. You have a primary alkyl halide that's adjacent to a carbonyl. This guy right here reacts 10 to the 5 times faster. What's 10 to the 5? Is that 100,000? 100,000 times faster than methyl bromide. So this is one of the most powerful SN2 reactions out there. Again, I don't want to spend too much time explaining that, but again, I want you guys to recognize that whenever you have alpha halo carbonyl systems, very good SN2 reaction. So you're absolutely right. This guy will displace that electron. Okay, so this is B. And now C does what? C employs a base. Followed by acid. I'll do it that way.
Tetrahedral intermediate? Oh, no. Base is going to deprotonate this alpha carbon. We have 2 of them, right? So once we deprotonate, we have nucleophile, which will attack a good electrophile. We don't have an alpha beta system.
So let's just do both of them. So what you're saying is you can attack either this proton, right, or that proton.
Yep.
Okay, so let's just do both.
Can you please pull your paper up, Professor?
So I'm first going to show if it attacks, let's call this A. Okay? So if I deprotonate here, remember this is an ester, so it should do nucleophilic addition. So this would be a 1, 2, 3, 4, 5. And because I have an ester, I'm going to regenerate that carbonyl. Okay? If I was to attack at B, let's try that. If I attack at B, it's going to attack 1, 2, 3, 4, 5. So I get another 5-member ring. And because this is an ester here, I regenerate the carbonyl.
Can you move the paper up a little, please?
Sure.
Thank you.
Okay. All right. What I want to do now is let's consider what happens in steps 4 and 5. So steps 4 and 5, and I'm going to relabel 4 and 5 as sodium hydroxide, water, followed by H3O+, and I'm going to put delta as my heat. Now, this is standard conditions here for what you learned with Dr. Schwann in chapter 22, and this is saponification of ester followed by decarboxylation. So if I do that for A looks like this guy. Where I lost the CO2 group there. Okay? I'm just going to say from A. From little a. If I do that for B, I get that.
Can you scroll up the paper, please?
I will. Just give me 1 minute. I'm writing. Let's do that. Is that better? Okay. So recognize, regardless of which direction I go, after decarboxylation, saponification and decarboxylation, I get the same product. So even if I got a mixture of this, it doesn't really matter because that final step, I have it. Now I can speculate and say that I would think that this B might be more acidic. Why would I say that? Because nitrogen is electronegative. It's going to have an inductive effect. Okay? Or on the other hand, I can say that, yes, this makes it more acidic, but once I form the enolate, there's a negative charge here. 2 electron pairs adjacent to each other will be destabilized. So I really don't know. I actually think it happens up here. So I actually think it, personally, I think it prefers to abstract the HA proton. But in the end, it doesn't matter. Okay? So consequently, the final step here, so this is D, either one of them. The last step is sodium borohydride. And sodium borohydride just reduces ketones to the alcohol. Okay. So it was just an example that I just wanted you guys to see where you're basically utilizing a bunch of reactions you learned. The first reaction is a new reaction, that's a Michael. The second one is an SN2, so going from A to B is SN2. B to C here, I guess this is C, is just kind of like a Claisen reaction, right? Where we're basically abstracting a proton and doing this is called a Dieckmann reaction, specifically. So Dieckmann, where we're taking a diester and making a ring system that, in this case, a 5-member ring. And then going from C to D is what you learned in chapter 22, and that is saponification, decarboxylation. And then finally, to the final product is just reduction of a ketone. Okay, so you can start seeing that you've learned a lot of reactions now, that you can start to recognize some of the pathways chemists have come up with to make a variety of different types of molecules. Okay?
I have a question.
Yep.